Hola amigos! In our last session, we saw some fundamental mathematical tools for solving the problems in electrostatics or magnetostatics or any other related electromagnetic problems. In this video lecture or in this session, we'll be seeing some topics until I think electric potential, right? I know the previous video was about 21 minutes and you might have got bored, but I want you to mention that in your comments. How do you feel about the video? Do you feel it feasible? Do you like the way I teach or I explain? Please comment. Thank you. Now, let's begin with our stage 2, that is Coulomb's law. Okay. So, before that I'll tell you one thing which is very strange, that Coulomb was a French colonel, and being a colonel, he devised this law. According to Coulomb, the force between any two charges, or the force exerted by a particular charge Q2 on Q1, is directly proportional to the product of the two charges Q1 and Q2, and inversely proportional to the square of distance between them. Since force is a vector quantity, the vector direction is defined by the direction vector from Q2 to Q1, that is RQ2 minus RQ1, right? Now, this is a proportionality constant which is K, and its value is 9 into 10 to the power 9 meter per farad, which is also given by 1 upon 4 pi epsilon naught. Now, what is epsilon naught? Epsilon naught is nothing but the permittivity of free space or air or vacuum. Now, the value of epsilon naught is nothing but 1 by 36 pi into 10 to the power minus 9. This is much easier to remember than this complicated numerical value. The unit is farad per meter. Let me tell you one thing, that the unit is very important in any of the physical quantities, right? Epsilon r is nothing but the relative permittivity of any material medium. For free space or air or vacuum, it is 1, right? Therefore, the epsilon, which is the permittivity of the medium or the material medium, is relative permittivity multiplied by the permittivity of free space, air or vacuum. In this case, epsilon r is 1. Therefore, epsilon naught will be equal to epsilon. Right? Now, this is the figure regarding it. So, F21 is nothing but the force exerted by the charge Q2 on Q1. The force exerted by charge Q2 on Q1 is nothing but F21. Right? And the direction of this charge is nothing but from Q2 to Q1. Right? Now, here let me make one correction. This is Q2, Q1, because our force is exerted from Q2 to Q1, right? So this will also be from Q2 to Q1, since our force is exerted from Q2 to Q1. So this is nothing but our Q2, Q1 is nothing but the direction vector from RQ1 to Q2. Oops, I think I made a mistake. Previously, it was written correctly. So I want you to learn from this mistake that in case of this particular force, since the force is exerted from Q2 to Q1, we'll be writing it as Q1 to Q2, the opposite way. So this is RQ2 minus RQ1. That is, the direction vector is from Q2 to Q1. So this was previously correct. Right? This has to be RQ1, RQ2. Now you don't make this mistake again. Okay. The next thing is, suppose if we want to calculate the force by a number of point charges or charges placed in a particular medium, we use this summation formula. So these vectors, the force vectors, get added upon each other, right? This can also be called as superposition theorem. That is, the force exerted by each charge on the other charge is the summation of all the other charges. That is, they do not interfere or do not affect each other's forces, so we can directly summate them. Next topic is electric field intensity and electric flux density. We will often use the term the electric field intensity as electric field, right? Now, electric field intensity is nothing but the ratio of force acted upon a particular charge divided by that charge. Suppose in our case, in the previous case, the force was acted upon Q1 from Q2. Therefore, the electric intensity at the point Q1 will be the force F21 bar divided by Q1 is equal to E bar Q2 to Q1, right? This is the general term for it. Now, the general formula for electric field intensity can be obtained easily by dividing the force formula by the charge upon which the force is acted. So here E bar is nothing but Q R minus R dash upon 4 pi epsilon naught mod of R minus R dash whole cube. Now what is R minus R dash? R minus R dash is nothing but, suppose if our charge is placed at R dash and the force upon which this charge is acting upon is placed at R. I'll tell you, suppose this is placed at R dash and this is placed at R. So we write like this. But if this is placed at origin, then R dash will be 0. Right? Now, you might seem confused about this particular form and this particular form of the formula. Sorry, here. This vector can be alternatively represented like this, right? This can be represented like this. From the vector formula, we know that the unit vector along any direction is nothing but the vector divided by its magnitude. The same concept is used here. For that, you have to see my previous video. Now, for line charge, that is, suppose you have a stick and you have all the charge filled upon it. This is my stick and I have the charges on it. But these charges are placed at infinitesimally small distances. So for that, I use integration, right? So suppose rho L is my linear charge density and dl is the length of a small element of this stick. Then I use this particular thing for representing my Q, right? So this is nothing but, as we know, Q by L is equal to rho L. So if I multiply by L here, I'll get Q. Simple. That's what is done here. So this is the formula for electric field intensity due to a line charge. AR cap is nothing but the unit vector directed from the charge to the point at which we have to measure the electric field intensity. Correct? So now similarly it goes for the surface charge density. We use rho s into ds, where rho s is the surface charge density and ds is the small area over the sheet of charge, right? Your third one is volume charge density, the electric field due to volume. The similar method which was used in the above two cases is also used here. Now, AR cap is the radial direction from that particular point and AN cap is the normal direction. In any surface, the surface is defined by its normal. So the electric field intensity at point P will be along the normal to the sheet or the surface. Now, these are some very general formulae for infinite line charge, infinite sheet charge, volume charge. If you place the limit in the above cases from 0 to infinity, you'll be getting these formulae. So it is very easy to obtain, but it is very, very important to remember as well. This is the concept of radial charge. That is the radial electric field. Suppose I have a charge in this particular ball, then the direction of electric field intensity will be radially outwards because of the positive charge, and it will be radially inwards for the negative charge. Now, electric flux density is nothing but the permittivity of the material medium multiplied by the electric field intensity. The same concept. The permittivity is nothing but the concept we saw over here. So I think you remember it very well. Now, this is the d bar is nothing but the flux density, but flux is given by integration of d bar dot ds bar. This is nothing but the dot product of the electric flux density and the infinitesimally small area ds bar over a closed surface. Now, this can be also written as the volume integral over rho v dot dv. dv is a very small volume and rho v is the volume charge density. So, if we use divergence theorem, we can relate d bar and rho v, which is like this. That is, rho v is equal to del dot d bar. This is Maxwell's first equation, and the equation is in its differential form. So for divergence theorem, you better look at my previous video regarding the vector fundamentals. Coming to the next topic, which is Gauss's law. This is the concept of radially outward and radially inward. For giving an analogy, I'll tell you that the radially outward charge, suppose you have a friend who is very good or very positive in nature. So he has the tendency to donate or to give it to everyone. But you have a friend who has a negative mindset. He has the tendency to take from everyone. Easy to remember, right? Maybe a silly analogy, but will help you remember things. Now, this guy Gauss, what he said was the total electric flux through any closed surface is equal to the total charge enclosed by that surface. Let me give you a very simple example. Suppose this is a ball, and I am holding a charge of 9 coulomb inside it. You understand that? The charge is inside the ball. Suppose here, this is my ball, the charge is inside the ball. Then the total flux or the total electric flux out of this ball is equal to this charge. That is, the total flux will be 9 Weber. Weber is the unit of electric flux. But if I place a charge of minus 2 coulomb outside, this will have no effect on the flux through this closed ball. So, to calculate the flux through any body, we assume a Gaussian surface or a closed surface, and we place our required body in that, and by using Gauss's law, we then find the electric field intensity through it. Now, for explaining this, I'll consider the electric field. I'll find the electric flux density due to a point charge. Suppose a point charge is located here. I consider a Gaussian surface, an imaginary Gaussian surface. Gaussian surface is always imaginary. That's what we imagine to simplify our problems. So, this is my Gaussian surface. I have to find the flux density through this. I know this particular formula. I know from the Gauss's law that phi is equal to q. Right? In the previous page, we saw the formula for phi here. Right? Now, I'll simply apply that formula here and use the Gauss theorem by replacing phi with q, and I'll integrate it and calculate the electric flux density. Here electric flux density is a vector quantity and can be given as dr ar cap. Dr is the magnitude of the electric flux density. The integration of small area ds is nothing but 4 pi r square, which is nothing but the area of a sphere, since we consider a point charge and we have considered a spherical Gaussian surface. By integrating this and substituting accordingly, we get d bar is equal to q by 4 pi r square ar cap. These derivations you can find in any of the textbooks and any of the books. But the important thing is to remember the formula of d bar. Here, 1, 2, and 3. If you get d bar once, you can easily calculate the electric field intensity by multiplying it with the permittivity of a given medium. In case of sheet of a charge, we assume a cube or a cuboid accordingly as our Gaussian surface, and then we calculate the electric field intensity by using electric flux density. For a volume charge, there are two cases. Consider this is a volume charge. I can find the electric field intensity inside as well as outside the volume charge. If I consider the Gaussian surface inside the volume charge, and if I consider the Gaussian surface outside the volume charge. Now, the volume charge here is a sphere. Sphere can be of two types. One can be a solid sphere. In a solid sphere, a spherical ball or a spherical, you can say something like a spherical ball or a ball of iron, which is solid, which has nothing inside it but only iron. The charge can only be on the surface in this case. It cannot be inside the surface. But if you consider a spherical ball, that is, it has a hollow space inside it, then the charge can be only inside the sphere, but it can also be on the outside of the sphere. Therefore, the charge can be inside and the outside, but it cannot be through the surface or inside the surface or inside the walls of the sphere. So, if there is a particular electric field intensity inside the sphere, it will not affect any point outside the sphere, because the electric field intensity cannot cross the conducting borders or the conducting material. So, if my field intensity is inside like this, it cannot cross outside. It cannot come outside. It will be blocked here, right? But similarly, the field intensity due to the external charge will be outwards or inwards accordingly, but it cannot go inside. It will be blocked here. This is a very important concept which is not very usually taught, but it is written in many of the books, so you have to be cautious and careful about this. So we get the formula of electric flux density in both the cases, and it is important to remember it to solve any kind of problems. This is the tendency of the magnitude of electric flux density against the radius r. Now, what is electric potential? Electric potential, before that I'll hope that you have a concept of work done from your basic mechanics. A small work done dW is nothing but the force applied multiplied by, or the dot product of a distance the particular object is moved, that is force into displacement. Now suppose the work is dW and the displacement is dl. We can replace F bar by QE bar from the definition of electric field intensity, and thus we can integrate it and we get this very important equation. And if we take Q on the left hand side, that is divide W by Q, we'll be getting the electric potential, right? So electric potential is nothing but the work done on a unit charge in bringing it from a particular position to a particular position. Usually the from particular position is considered as infinity. That is, we consider, suppose we are bringing the charge from B to A, we consider B at infinity, and therefore the potential at that point is 0 volt. Now you will imagine why this sign is negative. That is why VAB is equal to negative of this integral. The reason is because there is a loss of potential energy in bringing a charge from this particular point to this point, and the work is done by the electric field and the external work. Suppose I am pushing this charge from B to A, I have to do a work that is in opposite direction to the electric field. So if I'm opposing anything, that particular thing becomes negative, right? Now this is the general formula for electric potential. Electric potential is a scalar quantity, so we do not need any kind of vector to represent it. Now if I want to find the electric potential due to many charges, I'll use this formula. Very simple, you just sum it, and the formula for electric potential due to a line surface of volume charge is given by these integrals. the explanations and all you don't need very deep. If you're very interested in it, you can go through various textbooks. Now, this was the topic until which we have discussed today. If you want further reference, you can use the book Principles of Electromagnetism by Sadiku, and it is very good book. I usually refer it. You can also look up through the solved examples or solved problems, and if you want me to discuss any of the solved problems or any of the other problems on it, you please mention it in the comment. I'll try to solve your problems as soon as I can. And this is Shreyas Tawal signing off for today. Thank you. In the next lecture, we'll be seeing more of it.